This video contains a pink hippo puppet, examples about hearing loss, dating, and fake news. I say the word penis, but if you're offended by that, you'll be offended by this advisory. I'm physically assaulted by the aforementioned hippo.
Hello, and we're going to carry on today talking about the spine of statistics, and in particular we're going to focus on two concepts that people typically find quite tricky to understand, and that's because they're quite tricky to understand, and that is the standard error and confidence intervals. So in the previous lecture we started looking at what the linear model was, and we had a talk about parameters and estimation. And these form two of what I think are kind of 5 key concepts to understand when thinking about linear models. And they form the acronym of SPINE, hence the name of the lectures, the spine of statistics. And they are the standard error, parameters, which we've already talked about a little bit, but we're going to talk about a little bit more today. Interval estimates, that's confidence intervals, which we're going to talk a lot about today. Null hypothesis significance testing, which we'll leave for another lecture, and estimation, which we talked a little bit about in the previous lecture. So they have this lovely acronym of SPINE. They also happen to, if you rearrange the letters, have the acronym PENUS. But on balance, I decided to use the acronym SPINE. So we looked at this diagram last week, and this is our spine of statistics. At this point, you should become very, very grateful that I decided to use SPINE as my acronym and not PENUS, because if I'd chosen the other one, this diagram would have a massive penis in the background rather than a spine, and nobody needs to see that.
I really think you need to stop talking about penises. It's getting a bit weird.
Yeah, okay, fair point. So what we saw in this diagram last week is we can break the linear model down into a set of processes that are common to pretty much all the models that we fit. So we start off with a scientific question, we will then sample some data, we're going to talk a bit about that today, visualize the data, and then we fit a model. And having fit the model, we need to test whether it meets the assumptions that we made about the model, and we can also consider fitting a robust version of the model. So today we're going to be focusing on this part of this diagram. So we're still kind of honing in on what the linear model is, but in particular we'll have a look at, well, we'll talk more about how to interpret what parameters mean, but we're also going to start looking at confidence intervals. So when we talk about parameters, we're typically talking about what's known as a point interval, which is like a single value of that, or a single value that represents that parameter. Whereas you can also represent those parameters as what are known as interval estimates, where you're kind of saying the value is going to be somewhere between here and here. The other thing I highlighted on this diagram is sampling. So we're going to have a kind of an overview of some sampling theory, and yeah, we'll see how that all goes. So by the end of this lecture, what I hope in an ideal utopian world we will all have is an understanding of what sampling error is, an understanding of what the standard error represents conceptually. We will understand what confidence interval represents. We will hopefully understand what it does not represent as well. We'll understand that a parameter estimate is what's known as a raw effect size, so we can interpret it directly and it's going to tell us something interesting about our effect. And we're going to be able to hopefully interpret parameter estimates. We're going to look at some examples at any rate, and their confidence intervals, and also talk a little bit about standardized parameter estimates. So let's get into it then. It's going to start off just recapping some of the key concepts from the previous lecture. So we talked last week about the fact that most models in psychology boil down to, science more widely probably, boil down to a form of the general linear model, which is basically looks something like this. So we're predicting an outcome, and we're predicting it from a model that expands and contracts depending on how many predictors that you have. And that we also talked about the fact there will always be error in prediction. So models never predict individual scores perfectly. There's always error in prediction. And when we extrapolate from those models to kind of try and make general predictions about the world, there will be error in those predictions as well. Now, we also saw that when the form of the model is that we will have predictors, 1 predictor, 2 predictors, 3 predictors, whatever. We will have predictors, and each of those predictors is assigned what's known as a parameter. So this is a value typically represented by B, or at least in these lectures at any rate. And that is, and what that parameter represents is the relationship between the predictor and the outcome. So it tells us something about the direction of the effect and also the strength of the effect. And we also commented on the fact that when we write out these equations, we put hats on the betas. Now, partly that's because hats are cool. Everyone likes a hat, apart from the people that don't like hats. But they should like hats. Hats are great. But it's also to remind us that these are estimates. So that's basically why those kind of little hats are on the bees. We talked a little bit about what these bees represent. So we saw that a beta attached to a predictor, which I've denoted here by beta n, or bn I should say, is an estimate of the parameter for a particular predictor. So it's the direction and strength of the effect that that predictor had, or the kind of relationship between that predictor and the outcome. And that can also represent difference in means, as we will see in subsequent lectures. And we often have a beta 0, which is an estimate of the value of the outcome when all of the predictors are 0. And that's sometimes called the intercept. We looked at some examples of this. So we had an example of predicting how long people's ears ring for based on the volume of concerts they attend, or a concert that they attended. The form of the model is that we're predicting the number of hours that someone's ears rang for, and we're predicting it from the volume of the concert, and the volume has a B attached to it. And we saw some lovely photos of my wife and I at a very muddy concert. Now, looking at some, these are made up data for this, you can see that we can express the data points as a line. So it's kind of summarizing the data points as a line that is represented by the equation at the top of the slide. So we saw that the beta 1, the beta that's attached to the predictor, to volume, is showing us the rate of change, or the slope of that line. So the rate of change of the outcome as the predictor changes. So as the volume of concert increased, how rapidly did ears ringing increase or decrease? So it's a rate of change, or the gradient of the line. So bigger numbers mean bigger rate of change, bigger effect. And if that beta was 0, our line would be flat, and it would mean the rate of change was 0. So as the volume increases, ears ringing, or the amount of time the ears ring for, doesn't change at all. Looking at the intercept, we saw in this example, what we had to do is kind of expand the graph right out, because our data points, all our data points are at volumes above 90 decibels. So we'd have to go blub, 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 extend that line right back until the volume of the concert was 0, and we get an estimate of how many hours your ears will ring for if you were basically exposed to no decibels of noise at a concert. And we saw that we got a value of minus 37. And just to remind you, we talked a little bit about how that's a kind of nonsensical value, because your ears can't ring for a minus amount of time. I mean, I don't know, maybe they can in some kind of weird parallel universe. But, you know, it's not, it's a value that's kind of slightly strange. And it's worth bearing in mind that values from statistical models always think about their real world meaning. In this case, the real world meaning of that intercept is nonsensical. We also saw, as I mentioned, that these parameters can represent differences between means. So if we did a similar kind of bit of research where we had whether people attended concerts or didn't attend concerts, and we measured ear ringing, then what we're basically looking at is the difference between two groups. And in this case, Our beta 0 will represent the mean of one of those groups, and we'll come on to that in more detail in subsequent lectures. And the beta 1, the beta attached to the group membership, attendance or non-attendance, ends up representing the difference between those two means. Again, we will cover this in more detail. We also touched in the previous lecture on the fact that generally scientists want to make kind of broad conclusions. So as psychologists, for example, although, you know, it can be useful to be able to predict the behavior of like your mates in the pub, it's much more interesting to be able to predict the behavior of, you know, people in general. Although that's very tricky to do. So to take our example of you know, concerts and hearing loss, if we want to say something meaningful about the effect that concert volume might have on hearing loss or your ears ringing as we've operationalized it, then ideally we'd like to collect data from everyone that had ever been to a concert ever and measure their you know, hearing. If we could do that, which of course we can't, then we would have a kind of a population model. So we would know the sort of true effect that concert volume has on hearing. So this is what this diagram represents. This is a sort of hypothetical situation where if we could see the kind of population effect, it would look like this, or the population model. And in the population model, we can see that the parameter attached to our predictor is about 10. So what that's kind of telling us is that the relationship between concert volume and ears ringing can be quantified by the value 10. So in other words, as concert volume goes up by 1 decibel, we'd expect 10 more minutes of ear ringing, basically. Now that's the value we'd like to find out. We'd like to know that value. That's what we want to know. But we can't know it because we don't have direct access to the population. So what we do instead is we take samples. So let's say we take a sample. Here's our sample, and we use that sample, we fit the model, we use ordinary least squares estimation, which we talked about in the previous lecture, to estimate what those betas are. And as you can see, you know, there's a sort of similar pattern. There's a in the sample and the population. So as concert volume increases, ears ringing increases, and you can also see that the estimate we get is 9.94. So the estimate of the parameter for volume is 9.94, which is pretty similar to the population value, which of course we don't know, and we'd have no way of knowing it was similar, but you know, just showing you it's similar. And of course that's only one random sample that we could have taken. You know, there are lots of other random samples that are waiting around to be taken. And let's look at some sort of parallel universes where we took different samples. Here's 3 parallel universes where we've taken different samples. You can see in every sample, if you take random samples, you get something kind of representative of the population. So the relationship between concert volume and ears ringing is the same in all the samples. We're getting a kind of an upward sloping straight line showing you that as concert volume goes up, ears ringing goes up as well. And also we can see that we get estimates for the effect that are broadly similar to the population. They're not too dissimilar, but they are slightly different, and they're also slightly different to each other. So in each sample that we take, if we were to take multiple random samples, we would get slightly different estimates, and those estimates you know, may or may not be similar to the population estimate, the population value. So what this is illustrating is something known as sampling variation. So the estimates that you get in a particular sample will be slightly different to the estimates that you get in other samples. But you know, they should, in an ideal world, be representative of the kind of general population effect that we're trying to establish or trying to quantify. So let's have I'm going to kind of look at a very, very simple example now, where we don't have any predictors, we're just trying to estimate a mean. So this is kind of, in a way, it's the simplest model you can fit, because you're saying that, you know, for every person you predict a single value, the mean. And what we're going to do here, you may be wondering why there's a picture of me dressed as a slightly weird bearded zombie, but all will become clear in due course. So this example was inspired by some research that looked at people's performance on maths tasks, and they found that, I mean, it was a bit more complicated than this, but they found, broadly speaking, that some people performed better at a maths task if they did the task under a different name. And this got me thinking about dressing up as, like when I'm doing complicated stat stuff, of dressing up as Florence Nightingale, who was a very brilliant statistician, as well as being a very brilliant nurse. That kind of inspired, we got invited to a Halloween party a few years ago, and we had to dress up as kind of famous, I don't know if it was famous scientists, I can't remember, but anyway, but I chose to dress up as zombie Ronald Fisher. So Ronald Fisher is largely responsible for most of the statistical methods that we use. You know, bit of a dubious character, if I'm honest. So, you know, great on the stats front, not so good on the you know, ideological front, let's just put it like that. So, you know, if you're doing statistics and feeling really overwhelmed and you know, want to blame someone, blame him. And if you're kind of thinking, you know, he's like the devil incarnate, well, from a personality point of view, he kind of was. So anyway, less said about that, the better. And on the other side, my wife chose to dress as zombie Florence Nightingale. So we went as zombie statisticians. And like I said, although Florence Nightingale is probably more famous for her work as a nurse, she was actually a pioneering statistician as well. So here we are, dressed up, trying to make ourselves more clever at maths by dressing up as people clever at maths. So let's say you give us a maths task and we're interested in the accuracy on that task, and we're just going to predict it from the mean. So beta 0, an intercept. So there's no predictors, it's just mean accuracy is our predictor. So we're going to look at how sampling works just for a mean, because the mean is a parameter, but it just keeps things a bit simpler to talk about a single parameter rather than an entire linear model. So let's say that in the population, if you gave people this maths task, they would on average get a score of 50. So the population value is 50. That's the value that we're actually interested in finding out. But of course we don't have access to everyone on the planet. So we would take samples. And this is just illustrating that there's sampling variation. So if you were to take different random samples, it's really the same point we were making a couple of slides ago. If you take different random samples, you would get different estimates of the population value. So in our first sample, we get an estimate of 50. That's bang on the population value, but bear in mind we wouldn't know it was. Our next sample is 40. That underestimates it. Next one is 55, overestimates it. Next one's 55, overestimates it. Next one's 45, underestimates it. So two concepts this is illustrating. First is sampling variation. The estimates you get in different samples will be slightly different from each other. So there will be variation in your parameter estimates across samples. The other thing it's illustrating is sampling error. So there is often a difference between the estimate in the sample and the actual population value. So here in our first sample, the sampling error was 0. It was on the money. But in our second sample, there was some sampling error. So the population value is 50, but the sample estimated as 40, or it was estimated in the sample as 40. Now, if you were particularly, so I'm talking very hypothetically here, this is not something you'd actually do in reality. So we're just kind of doing a sort of mental experiment, if you like, where we go crazy for sampling. Like we love taking samples. So we take some more samples. So we've now got 2, 4, 6, 8. We've got 9 samples here, and you can see the concepts that we just illustrated, which is that there's sampling variation. The samples are all giving us slightly different estimates of the population value. and also that there is sampling error. So some of the samples are not getting exactly the population value, they're giving slightly different estimates. But the thing is, if you were to take lots and lots and lots and lots of samples and you plotted the estimates in the samples, so in this case we took the mean in all the samples and we plotted a frequency distribution of the means, that's what the red plot at the bottom is, we would find that the middle of that distribution is the population value. So, for example here, our first sample, the estimate is 45, second sample, the estimate is 50. Next one is also 50. We've got one over here that's 50. So we've got, that's bad drawing. So we've got 3 samples that give us an estimate of 50. So that's this middle bar here. We've got a sample that gives us a value, an estimate of 40. That's this bar here. We've got one that gives us an estimate of 60. That's this bar here. So you get the general picture. So we're building up a kind of frequency distribution of the different values. And I've kept the number of samples relatively small, but if you imagine taking like thousands of random samples, you could build up this frequency distribution. And what we would find is the middle of that frequency distribution, this value here, look at what it is. It's actually the population value. So sampling works because across lots and lots and lots of samples, the average of those samples, on average, the samples will give you the population value. But the particular sample that you have might not give you the population value. But on average, samples give you the population value. So what we've got down the bottom here, which is a distribution of sample estimates, is what's known as a sampling distribution. So when you hear people talk about a sampling distribution, it's a kind of it's kind of like a theoretical distribution, really, because you wouldn't ever really go out and collect like hundreds of thousands of samples. So sampling distribution is kind of a theoretical entity. It's kind of like, it's like a unicorn. It's like this precious, sparkly thing that flies through the air, that you that you'd love to see, but you can't, unfortunately. Anyway, enough of that. So sampling distribution, it tells us what the, kind of what the variability is in estimates across your different samples. And crucially, if we were to look at the standard deviation of this sampling distribution, this tells us something about how much variability there is in estimates across samples. So if you imagine your sampling distribution, we'll talk about this a bit on the next slide, but if you imagine your sampling distribution is very, very narrow, so it has a small standard deviation, then what that basically means is all your samples are giving you very, very similar estimates. Whereas if your sampling distribution is really, really spread out, then it's telling you that your samples potentially have very, very different estimates. And when you look at a standard deviation of a sampling distribution, it's actually called the standard error, not the standard deviation. Okay, so let's kind of recap that idea a little bit by looking at 2 different scenarios. So we've got a red population and a blue population. The red one is on the left as you're looking at the screen, and the blue one's on the right as you're looking at the screen. So let's take the red one first. So again, just imagine each of the circles coming out of the population is a sample, and we've got a value in each circle, which is the estimate of the population value. So in the red one, our first sample gives us an estimate of 45, second one estimate 50, next one 50, next one 40, next one 55, and so on. And imagine again that we created a a frequency distribution of those estimates, and you can see that's the red frequency distribution below. Again, that frequency distribution is centered on 50, so it's centered on the population value, but particular samples may be close to that value or not so close. So for example, if you'd happen to have sampled this sample, then, which is down here, then your estimate's actually quite far from the population value. But on average, samples are going to give us the population value. So if we look at the spread of these estimates, so the spread across these kind of, the spread across all these samples, so the spread of these values across all these samples, it's 6.12. And again, because this is a sampling distribution, this is actually referred to as the standard error, not the standard deviation. So 6.12. Estimates are fairly spread out. Now let's look at our blue population. So we got we can compare these because it's the same scenario. So the mean in the population is 50, but we've got different estimates in our blue samples. So our first sample gives us an estimate of 50, the next one 54, 48, 50, so on and so forth. Again, we plot these in a frequency distribution, and hopefully by comparing the two frequency distributions at the bottom, you can see that on the right hand side, the distribution is much narrower. So the kind of the range of estimates, or the spread of estimates across samples, is much narrower, which means that our sample estimates are kind of closer together, and it also means that they are closer to the population value, because again, the population value just splits this right down the middle. And if we look at the standard deviation of these estimates, which we've just seen is the standard error, it's smaller. It's 2.45 rather than 6.12. And the fact it's smaller tells us that estimates across samples in this population are kind of closer together. So the estimates are more similar for the right-hand side than they are for the left. Now, one thing to know about sampling distributions is, and in fact this might be obvious from the previous slide, if you look at the previous slides, those distributions look kind of sort of normal, don't they? Now, just to remind you what a normal distribution looks like, normal distribution has a very kind of characteristic shape where at very, very small scores, the frequency with which those scores occur, so down this end, frequency is very small, and very, very high scores do not happen very often. So the frequency of high scores, so around here, is also very small, and you get the bulk of scores occurring kind of in the middle of the distribution like this, and it's symmetrical down there.
You're at it again. What's wrong with you?
Sampling distributions are typically normal, so they typically have this characteristic shape as long as your sample size is big enough. And the central limit theorem just basically says that if your sample size is bigger than 30, theoretically at least, then the sampling distribution will be normal. It will have the shape of a normal distribution. Now, there are situations where actually samples of 30 do not guarantee normal sampling distributions, but we'll save that for another day. So sampling distributions typically normal. One thing we know about a normal distribution is that if we standardize all the scores, so if we express the scores as standard deviations, then 95% of scores will fall between minus 1.96 and 1.96. So another way to say that is that 95% of scores will fall between minus 1.96 standard deviations and 1.96 standard deviations from the central value, or from the mean in this case. So we can actually use this to start thinking about expressing estimates as intervals. So let's say rather than expressing our estimate as a single value, we wanted to have some kind of interval. we could think about how to construct an interval such that we're reasonably, or we know that in the long run, across a certain number of samples, we'll hit the population value. And that's basically what a confidence interval tries to achieve. So imagine you've got your sampling distribution. It looks like this. And let's say that we know, based on the standard error, or the spread of estimates across samples, we know that 95% are going to fall within kind of a certain limit, basically, based on the fact that that distribution is normal. So what we could do is think about how wide would the interval need to be to kind of hit the population value a lot of times across different samples. So let's imagine we take a sample and we choose this to be the interval. So we choose the blue line to represent an interval around that single value. So the single value, the single estimate is, say, about 46, and then we just put a kind of width around it. Now, what should that width be? Well, what we can do, let's say that we wanted to create a 95% confidence interval. We could say, well, we know, because the sampling distribution is normal, that 95% of scores will fall within 1.96 standard errors of the center, because it's normal. So that's a property of the normal distribution. So let's do that. So we make this interval 1.96 standard errors on each side of the point. So we stretch the line out to 1.96 standard errors either side. So what we see here is when the point falls within the boundaries of 95% of scores, then we are going to hit the population value, because that interval crosses that line at the center of the sampling distribution. Let's take another sample. This one falls outside of the range within which 95% of sample estimates fall. And we can see in this case, its interval misses the population value. And let's take a third one. And this one is right on the very edge. It's right at the point at which, or right at the limit within which 95% of scores fall. And at that point, it kind of exactly touches it. So what this means is across lots and lots of samples, if we were to set the limits around the point estimate, if we were to set the limits around the estimate to be 1.96 times the standard error, we are going to hit the true value, the population value. We're going to hit it in 95% of samples, because remember, it just about hits it. The confidence interval just about hits the population value when it's right on the edge of that boundary within which 95% of estimates fall. If it's lower than that, if it's a sample that has an estimate lower than that limit, it's going to hit it. And if it's outside of that limit, it won't hit it. And we know that it's only going to be outside of that limit 5% of the time, because we know that 95% of sample estimates will fall within that 95% range. So by setting a limit around the point value, which is 1.96 standard errors, we know that 95% of samples will if we set this interval, then in 95% of samples we will hit the true population value, and we will miss it in 5% of samples. So that's basically what a confidence interval is. So what we've got here is a little app that you can use in my Discover package for R. So I've just set a population to have a mean of 0, and what this app does is shows you, it just takes random samples from that population, constructs the confidence interval, and kind of shows you what happens. So each one of these bars appearing is a new sample with a new estimate and confidence interval around that estimate. And what you can see is most of these confidence intervals are hitting the population value. That's the line down the middle, and they're coloured in blue, but some of them miss. So the orange coloured confidence intervals are samples where the confidence interval misses the population value. And what you'll see, there's 100 samples being taken here, and actually 95% of the confidence intervals capture the population value. We're going to try this again. What I'm doing here is just flicking through and taking another 100 samples, but I'm just not animating it. So you can see the next time we take 100 samples, we have again 95% hit it, but then the next time we only have 93% hit it. Then we have 95% hit it, next time around 95 again, and 95 again. What this is going to illustrate though is that the 95% is a long-term value. So over kind of an infinite number of samples, 95% of the confidence intervals contain the population value. So what confidence intervals are? They're intervals that contain the true population value of the parameter in 95% of samples. It's worth going over a few things that they're not, because like I said, people find confidence intervals very confusing. So to help me out here, we have a bit of role play with Professor Hippo.
Hello.
How are you?
Grumpy.
Why are you grumpy?
Because people keep misinterpreting confidence intervals, and I don't like it.
Okay. Well, let's see what happens. So, you meet Professor Hippo at a party, and you want to impress him with your statistical knowledge. Say, I found out what confidence interval is today.
Oh yeah? What is it?
95% confidence interval.
Yeah, tell me.
It's an interval where I'm 95% confident that the population estimate falls within that interval. That's what it is.
Oh. No, it's not. It's an interval that contains the true population value of the parameter in 95% of samples.
Okay. I also think it's an interval where there's a 95% probability that it contains the population value.
No, no, no!
So, in case you ever come across Professor Hippo, let's be clear about what confidence intervals are not. There's not a 95% probability that a given interval contains the population value. In fact, for a particular sample, your interval either contains the value or it doesn't contain the value. So the probability is either 0 or 1, but you don't know which it is. It is also not an interval that reflects your subjective confidence in the value of the population parameter. So avoid those kind of common misconceptions. Okay, just to close off, we're going to have a look at how we interpret these. Having estimated these parameters and their intervals, how do we interpret them? So we've got an example here of some real data of a study that looked at whether playing hard to get in a kind of dating context was a good strategy. So broadly speaking, they had some participants, and those participants were kind of chatting over instant messenger. So actually there was one participant and the other participant was actually a confederate. So, they were kind of told what to do. And after the 8-minute chat, the participant was asked to send a final message. And that final message was coded for the number of expressions of romantic interest, which in this study ranged from 0 to 4. What they also did was they asked participants to make some ratings about how hard to get they thought the person they were chatting with was. So these were 3 items. An example of the item is the other participant is hard to get. I mean, it sort of does what it says on the tin, really, that item. And they rated it as 1, not at all, up to 5, very much so. And they also rated the mate value. So these were 4 items, and one of those items was, I perceive the other participant as a valued mate. Also kind of does what it says on the tin. And they were rated again from 1 to 5. So here's the actual data from one of the studies, and we can see what we're trying to do here is we're predicting these interests, the expressions of interest, which varied from 0 to 4, and we're predicting them from the ratings of hard to get. So we're just looking at one of the other variables at the moment. And there's the data. You can see there's a positive relationship. So the more, as the perception that the stooge was hard to get increased, expressions of interest also increased. Kind of looks like playing hard to get is a good strategy if you want to increase someone's interest. When you actually fit the model, the value of the beta attached to the variable hard to get is 0.294. So that's the highlighted value there. So the way we would interpret this is as the perception of the other person being hard to get increased by 1, and bear in mind that's 1 on a scale from 1 to 5, 0.294 more expressions of interest were made. So the thing is, you can interpret this very directly. It's what's known as a raw effect size. It has direct meaning. So you can actually say to yourself, is it meaningful that as someone, as like a perception of hard to get increases on a 1 point on a 5-point scale, is it meaningful that expressions of interest increase by 0.294? I mean, obviously you can't increase your expression of interest by 0.294. Expressions of interest are whole numbers. What we could ask, though, we could sort of switch this around a bit and say, well, how much would you need perceptions of hard to get to increase by to get like 1 additional expression of interest? And basically it's 3.4. So to get 1 more expression of interest in that final message, you would need someone's perception of hard to getness to increase 3.4 on a 5-point scale. So it has to increase like more than half the length of the scale. So I would argue this is, although it was nearly a significant effect, I would argue this is quite a small effect. It's not in the real world. It's not that kind of powerful effect to, if you've got to change someone's perception of you being hard to get almost, or like I say, like over half the length of the scale that you're measuring it on, just to get 1 more expression of interest. That's probably in the real world not a very strong effect. This we can also construct a confidence interval around this effect. So this is what we've done here, and I've highlighted the lower value and the upper value of this interval. And the way we would interpret this is to say that, assuming that this sample is one of the 95, this is the easiest way really to interpret confidence intervals, I think. Assuming that this sample is one of the 95% that yields a confidence interval containing the true value of the parameter, and I put it in red because we're making that assumption, as the perception that the other person was hard to get increases by 1, the corresponding change in the number of expressions made could be as small as minus 0.036. So at the smallest extreme, that's how small the population effect could be if we make the assumption at the beginning. In other words, there could potentially be fewer expressions of interest as playing hard to get increases by 1. At the other extreme, so at the high end of the confidence interval, is the perception of hard to get increases by 1, the corresponding change in the number of expressions could be as large as 0.6. So here we're sort of looking at needing less than a shift of 2 on our 5-point scale to get an increase of 1 expression of interest. So still, not a dramatic effect, but at its extreme, it's certainly bigger. Now, critically, this confidence interval also contains 0, so it's plausible under the assumptions that we're making that as the perception of the other person being hard to get changes, there's no change in expressions of interest. In other words, there's no effect. But all of those interpretations are true only if our initial assumption is correct, and that assumption might be false, and we don't know whether it's false. But in the long run, if we use this interpretation, we will be wrong 5% of the time and we'll be correct the other 95% of the time. But it is always worth remembering that if we interpret confidence intervals in this way, we should be explicit that we are making an assumption at the beginning. And bear in mind, we saw last week what happens when the assumptions of your models are wrong. It can be a disaster. Finally, so that's looking at model parameters as raw effect sizes. Sometimes you'll come across what are known as standardized parameters or standardized effect sizes. So this is basically where instead of fitting the model to the raw data, you fit the model to the raw data expressed as z-scores. So they've been standardized. Everything's expressed in standard deviation units instead of the original units. So an example of this, again, this is some real research, real data from an actual study, looking at what predicts belief in fake news. So what they had some fake news items that actually kind of existed in the world, and they got participants to rate them, so 12 of them in all, from 1 not at all accurate to 4 very accurate. They had lots of other like some actual non-fake news and things like that as controls, but we're not going to look at that. They also gave them a questionnaire measure of delusional thinking. So this had items such as, do you ever feel that there is a conspiracy against you? So that would give you some kind of indication of a person's propensity to delusional thinking. And they also gave a measure of critical thinking. So they had 7 problems that had intuitive but incorrect responses. So you basically need to think about it to get the correct answer. So one example of this was, how many cubic feet of dirt are there in a hole that is 3 feet deep by 3 feet wide by 3 feet long? Give yourself a minute to think about the answer to that. Now the intuitive response to that is to go 3 times 3 times 3, 27. But of course that's the wrong answer, because in a hole there are no cubic feet of dirt because it's a hole. So they had these measures, and we're just looking here at belief in, we will come back to this example in another week, but we are trying to predict fake news beliefs from delusional thinking. You'll notice my B's have changed to Greek betas. That's because I want to represent the fact that they're standardized, and because we're working with standardized measures, the intercept actually ends up being 0, so we could in fact cross that out, but I thought it might be confusing if I didn't put it in there. So what we have here is we have a standardized beta, so this is beta but expressed in standard deviation units of 0.242. And the way we can interpret that is, for every standard deviation change in delusion proneness, belief in fake news increases by 0.242 standard deviations. So, I kind of think the raw betas are much easier to get your head around, but with standardized betas, you can compare them across studies because everything's in standard deviation units. But intuitively, it's difficult to think, I think, in standard deviation units. But anyway, you will see these quite often. So just to summarize, this is one of a series of lectures where we're looking at the spine of statistics. We talked about parameters and estimation in the previous lecture, And today we talked about interval estimates. So any parameter you estimate, you can construct an interval estimate as well. And typically people use confidence intervals. There are other types of intervals that you can use that we don't talk about on this module. And these confidence intervals might, under certain assumptions, tell us something about the true value of the parameter in the population. And we also talked about the standard error of a parameter. And the standard error tells us about the variability in estimates from sample to sample. It's also used, because it tells us about variability across samples, it's used to construct the confidence interval. And we will see next week that significance tests also rely on the standard error. So the standard error is a really important statistic because, as we will see in a few lectures' time, if the standard error is incorrect or biased, that has a knock-on effect on the confidence intervals and significance tests, which we'll talk about next week. Okay, thanks for your attention. Bye.